All right, well, welcome everyone. Thank you for coming today. The name of this talk on paper is Experimental Mathematics via Machine Learning. So I didn't want to put the other part on the official brochure, but the question that's sort of always plaguing my mind is are mathematicians at the risk of extinction? Sort of the question that everyone has to ask themselves in the age of AI and its rise is whether or not AI can do the things that we have traditionally thought of as the mathematician's role. So this talk is going to have sort of two halves today. One is catching up to the state of affairs, and then the second half is sort of what happens next. So to go back into the ancient history of computers and mathematics interplaying, we go all the way back to 1976. And this is sort of widely regarded as one of the first instances where computers contributed to the proof of a mathematical theorem, even if it isn't viewed through today's standards as machine learning or AI or anything like this. So one thing I want to stress right from the start is there's going to be a lot of math from all kinds of different fields of mathematics, and none of these slides are really about the content of the mathematics. It's about the interplay between the math and the computers. So if you get to a slide where you don't know what any of the words are, it's not the end of the world. The point is to see how the computers are helping us think through those problems. But this one is a very understandable question. So say you're a cartographer back in the 1800s and your leal lord has decided that he's going to task you with making a map of the kingdom, or in a more modern setting, the country. This is a theorem about maps being subdivided into smaller parts. So here's a map of the country divided into counties, but it is nothing special about the US geography. It is anytime you have a map divided into smaller parts. And if you are a cartographer, a map designer, or maybe the assistant cartographer who has been tasked with coloring this map, you need to know when you go out to Target, do you buy the 128 color pack Crayola thing, or do you buy the smaller 8-pack? And the theorem is a pretty remarkable theorem that if your constraints are to color the counties of this map in such a way that two counties have to have a different color if they share a border, then you only need 4 colors. So this is not special to this map in particular. Of course, you can demonstrate it for any particular map by actually coloring it in. This is a statement for all maps. So as long, because you don't want two counties sharing a border to share the same color, then they look like they blend in. So this is cartography 101, people. This is basic stuff. So, four colors suffice is sort of the tagline of this. This does not, if you are not in the world of mathematics, feel like a mathematical theorem, right? It feels like coloring for children rather than what you typically view as mathematics. Here's how we embed it as a mathematical problem. This is the broadly speaking, this is the realm of graph theory. Graph theory studies pictures that look like this. So here's how you convert it to that problem. This graph does not represent this county map, but in principle, what you would do for this county map is you make dots and edges, just like this picture on the right, where for each county you put a dot, and if two counties share a border, an edge, then you connect those two dots. And now the question of coloring the map turns into coloring the vertices in this picture, and the question now feels a more mathematical one. Given a graph, some dots and edges like on the right, can you color the vertices always so that two connected vertices don't have the same color? And this has a storied history, this result. This was believed to be true in the 1850s. It was claimed to be true later that century, 1880s, 1890s. And it wasn't until maybe 50 or 60 years later that people noticed that there was a gap. Like it was just a wrong proof. And we had to sort of retract all of our belief that this was a known fact. And the first actual proof of this was by these two mathematicians, Appel and Hawken, in 1976. And the way they approached this was on the graph theory side. They were able to demonstrate that if you were a problem graph, a graph that required more than 4 colors, your graph was in one of 1,834 special cases. So you could write them all down, and what they did, this is the first use of computing power really in a mathematical proof, is just to brute force through all of them. You run some code to go through all 1,834 bad cases and check that in fact you could do it with 4 colors. And the next slide is this is just a screenshot from that paper. It was them summarizing 15 of the 1,834 cases. Okay, so there's some big philosophical questions attached to this result. Again, we're not claiming that the coloring of maps is like the dire need for, artificial intelligence and machine learning. But there's a question as to whether or not this benefits society, right? Benefits humanity, benefits mathematics. Did we learn anything by this proof of this result? In general, mathematics, we don't want to know that something is true. We want to know why something is true. And a proof by exhaustion of all cases might not rise to that level of standard. Okay, I'm going to fast forward 20 years to another example, and I'll stress again that if this is not content that's familiar to you, that's not a big deal. The question is whether the computing aspect of it was beneficial. This is arguably the first time a computer proved something rather than aided in the proof of something. And the context here is sort of propositional logic. If you've seen these symbols before, think of the V as an or, and think of the like squiggly thing as a not symbol. This is the mathematics of Boolean algebras, which you might see in computer science. And the question was, if you assume those first three lines, if you assume three axioms, can you deduce this other? So that's the question. It's a very easy to state question, but all of the modern logicians at the time could not prove this. Okay, so this was a big open question. And I told this to my students at the start of a semester each time, when you don't have much material, there's not much for you to do. Like in the day one of a class, you only learn 2 facts, so every homework problem is going to require only those 2 facts. This is the same sort of thing in this situation. If you want to prove that this one thing follows from these 3 things, every possible proof looks roughly the same. There's some combination of those 3 steps in some order. And that's something that is computerizable in a sense. And so the punchline to this problem is another computer proof, but to me, it's much more deeply philosophical than the previous. The previous one was a computational result. The way that this proof worked, it's still brute force, but it's a brute force through every possible proof. Okay, so maybe the proof of the thing goes axiom 1, axiom 3, axiom 2, axiom 1. Nope, that didn't work. Let's try 2, 2, 3, 1. Nope, that didn't work. But a computer can run through every possible combination, and eventually it stumbled on. I mean, maybe the result was false, right? It was a conjecture at the time, nobody knew the answer. You could try the first 1,000,000 proofs and find they don't work, and then you're not sure. But they found a proof. And the proof was so long and complicated, not because there was deep mathematical thinking, but because the series of expressions you got out in this proof got longer and longer and longer before it started to simplify down, that it's not surprising that a human just didn't have the energy to go through it. So it's a sort of a bizarre part in the history of mathematics where it's maybe the theorem was unprovable by humans just because it was so boring. Like, it's just so, like, no one had the stamina to work through all the calculations. And there's a place, again, where computers might be able to help. One thing I really want to stress, both of these starting examples are to stress 2 specific points. The first example was to stress that the goal is not to know that something is true, but why something is true. So the ultimate end goal should be a better enriched understanding of the structure. And this one, I really want to stress the small parameter space. It is because the only inputs we were allowed to use there's only 3 of them that were able to make computers do sort of our bidding with the early computers of, I guess, 1996. Okay, so now I want to jump forward in time. We are all bombarded daily with stories of new things that artificial intelligence can do, new things that we have to watch out for as we see, fake images generated, or we have, plagiarism questions or ethics questions about use of AI and things like that. So, and in particular within mathematics, we see a rise of the ability for artificial intelligence systems to solve homework problems or research problems that are much harder than they were able to do before. That said, it's not there yet. And there's been a sort of a meme running around the internet that perfectly encapsulates this. Over the last couple of weeks, the following prompt has been thrown at ChatGPT many, many times, and it's had the same answer for every person. How many R's are in the word strawberry? And it tells you that there are 2 R's in the word strawberry. And if there are any linguists in the audience, you will note immediately that that answer is incorrect. There are, in fact, 3 R's in the word strawberry. And it is, ChatGPT is not a counting model, it's not a math model, it's a language model. So it tries to generate sentences that sound like something someone would say in response to that question. Yet it's usually pretty find. Usually if you force it, you say, could you check again? I'm pretty sure there's 3. It'll say, oh, I'm so sorry, you're right, I've checked my work. There really is 3 R's in the word strawberry, but it is remarkably steadfast that there are only 2. Yes. So if you're listening online or if you ever computer here and you get bored, just go open ChatGPT, see if you can try to convince it that there are 3 R's in strawberry. It is challenging. One thing to note about ChatGPT is it has a lot of internal submodules, and one of its tasks when it receives the question is deciding which submodule to send it out to. So one thing you can do to try to prompt engineer or prompt hack ChatGPT and tell you the correct answer is to sort of force its hand into something more logical oriented than language oriented. So here's an approach. We say make a history of the frequency counts of all the letters in the word strawberry, and it correctly diagnoses this. Why does it do that? Because it's not using its language center, it's generating Python code and running that Python code and then spitting out the output. So if you click on the little blue part at the bottom there of the histogram, it'll tell you the work it did to produce this image, and that's the source code for that. Okay, so that's correct. So we forced its hand, and now we say, okay, you've done this according to the histogram that you just produced. How many R's are in the words? It doesn't even back off and insist by counting. It literally says, according to the histogram, there are only 2 R's in the word strawberries. So again, if you want to try this on your own, it's a fun exercise to try to convince it. I did manage to get it to say there are 3 R's in the word strawberry, but the way I got it to do it was to say, I don't care if it's wrong, just please tell me the word strawberry. And it was willing to acquiesce to my demands. Okay. So, I mean, what's the takeaway? Like, this is not to mock ChatGPT. It is obviously much stronger in capability than this one example is making it out to be. But it does suggest that we have to be careful about how we process with math inside of it. And it's not designed for math, right? It is not designed to do mathematics. And so it puts us in a position that math has been in for 30, 40 years, which is trying to figure out what to do with the increasing level of mathematical sophistication of devices. Right? Because originally it was, 4-button calculators, and there was TI-82s, and then there were TI Inspires. Now there are computer algebra packages, and there are apps where you can scan a problem and it'll solve for you immediately, and we have to figure out what to do with all those. Probably the sort of hallmark of these right now is Wolfram Alpha. Wolfram Alpha is a website where you can go. It has some natural language processing, so you can ask English language questions like, what is the derivative of x squared plus 5? And it knows that you're asking a question and knows how to answer it. So that has an embedding into ChatGPT, and it is remarkable. So here's a sample prompt from ChatGPT with Wolfram Alpha plugged into it. The prompt was, evaluate the double integral of x, that's like e to the x of negative x squared minus y squared over the entire plane. And note that I was pretty ambiguous, like the entire plane is something that a few years ago, a computer would have balked at and said, I don't know what you mean by that, please define the entire plane, but it knew what I meant. And this is a pretty standard sort of advanced problem from Calc 2 or medium level problem from Calc 3, and it handles it no problem, both in terms of understanding what I'm saying, getting the right answer, which is a cool right answer, by the way. You're integrating an exponential and you're getting pi. Like, where did pi come from? And 3, explaining it, right? It does a good job of saying where each of those steps, where each of the components of the answer come from along the way. It says, oh, change the polar coordinates, use that formula, et cetera. Okay. So, anyone guess what happens next? We ask it, how many R's are in the word strawberry? It still believes there are 2 R's in the word strawberry. I suspect this is still its own internal mechanism for which subroutine to send it to, and it did not send it to the Wolfram Alpha subroutine, but instead used natural language processing to do it. But of course, that is part of the goal, right? ChatGPT is supposed to be triaging the request correctly to the right subroutine. So we have to take these into account. Okay, so the Wolfram Alpha part is a very strong computational tool. It leaves open the question of whether or not we can handle advanced mathematics. So, I mean, of course, Calculus 2, Calculus 3 is pretty advanced, but not research level mathematics. So I don't know if other people have ever had this situation, but sometimes you're about to give a talk on a subject, and the day before you're supposed to give that talk, there's some revolutionary change in that field. that alters everything you were going to say about the topic. That happened yesterday when, in response to this sort of like internet mockery of OpenAI and ChatGPT, they released the strawberry model of ChatGPT in response to these observations. So this was yesterday, introducing ChatGPT strawberry. That's an unofficial name for it. I'll talk more about the official parameters of this later, but you'll note that it correctly diagnoses the number of R's in the word strawberry. Moreover, you can see that it's more structured in its approach. Okay, so it thought for 5 seconds, and I will say this on the next slide, but one of the hallmarks of this new model is the deliberateness with which it spends extra time to think. Right, the standard ChatGPT model will spit out a 3-paragraph essay in the blink of an eye on whatever topic you want, just by fluffing it out with random sentences. It forces itself to think longer, and we'll see this in more interesting mathematical examples in a second, but it tells you what it's doing along the way. There's not much it can tell you what it's doing along the way when it's counting 3-letter R's, but even here it tries to say, I'm understanding the task, I'm actually counting, and I'm spitting out the answer. Okay, so if this model can do this, can sort of reason a little bit more than just generate, then we got some questions. Can we ask this sophisticated mathematical questions get answered? All right, so here's where I really will dive off the deep end in terms of mathematical content. And I don't want you to stress out about, oh no, another slide first. Okay, so this is their own description. So this is like a press release version of this. Learning to reason with learning language models. This is their goal, that instead of spewing stuff out, they are developing a reasoning mechanism. And they cite some pretty impressive stats. So the way that they're justifying their claim that, this is a new benchmark is by having the strawberry model take tests that are usually challenging for humans, even in that discipline. So they mentioned 3, there's a competitive programming competition. There's the USA Math Olympiad qualifier called the Amy exam for like seniors in high school. And then there is, I don't know the GPQA. Actually, you know the GPQA? No, I never heard. So anyway, so some sort of benchmark test for challenging problems in physics, biology, and chemistry. And they cite their model's success in solving problems in these exams. So here's just one. Here's problem 4 from the Amy from 2014. John and Steve ride their bicycles along a path that parallels 2 side-by-side train tracks running east-west. John rides east at 20 miles an hour. Steve rides west at 20 miles an hour. 2 trains of equal length in opposite directions at constant but different speeds pass the 2 riders. Each train takes exactly 1 minute to go past John. The westbound train takes 10 times as long as the eastbound train to go past Steve. The length of each train is m over n miles, where m and n are relatively prime positive integers. Find n plus n. So as you've no doubt worked out by now, the answer is 49. And the strawberry model gets this in like 10 seconds. So it spits out not only the correct answer, but it spits out a chain of reasoning that you can follow. They are generally more complicated than these sort of officially published solutions, so they don't always find the best path, but it solves it, and it solves it as well as the best and brightest of the high school students do when they compete on these things. Okay, so it's good. Like, it's reasoning, it's being able to solve problems. Here's where I started to say before. Here's where we're going to sort of dive off the deep end in terms of complexity. If you don't know these words, this is not a problem, but these are research questions, types of research questions that I run into like almost daily, because I'm supposed to know this stuff and I don't, so I have to like try to remember it. I'll just read the question. If 2 elliptic curves defined over a quadratic field have isomorphic mod p representations for some prime p, must the 2 curves be isosceles? So when I run into a problem like this, I will probably spend a few minutes trying to answer it myself. I will give up and get frustrated. We'll go find a reference, a piece of paper or a book that might have it. Invariably, I won't. I will try calling a research collaborator who's smarter than me and see if they know the answer. And all in all, it can take 1 or 2 hours. And if I get lucky, it might be just something I forget about for a while and come back to it. But the strawberry model was able to answer it in 16 seconds, which I feel proud of, because that's like 10 seconds longer than it took to answer the Amy problem from the Olympiad, and it just says no. And I've only included one shot here. I'll put another screenshot in just a second, but it's 6 screenshots worth of content. In fact, it suggests like learning growth for me. It sort of suggests things I might have wanted to think about when I was asking the question in the first place. Here's some related content you might like to know about as you proceed with whatever study you're interested in. And also, it gives me the references that it has used to get this.
Did you ask it for example?
Yes.
Counter example.
I believe in this case it did. That one of the 6 slides it said, here's a curve, here's a field, blah, 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 blah. Which is very frustrating. Okay, but actually though, okay, I will confess that at this point, remember this was just released yesterday. So over the last 24 hours, I've had a mission to get it to be wrong about something. So to prove that, remember the subtitle of the talk was, are we going extinct as mathematicians or something like that? I wanted to convince myself that I was not. And I figured that now that it has access to references, my best bet was to use my own research, my own mathematical research, and see if I could beat it at the one thing I'm like an expert in. So I asked it what it knew about my own research, and I'll save you all this stuff and just read the last little bit at the end. It notes the absence of my mathematical research. I'm realizing that there doesn't seem to be any information on a mathematician named Cameron McLean in the data. Very demoralizing, and they really rubbed it in. But it's that's all the more promising for their existing stuff that I know that it doesn't. So we will try this out. I asked it a question it's actually a graph theory question, the same graphs as in the second or first slide of the talk, second slide of the talk. Again, the words don't matter here, but the question was, suppose H is an R-regular graph on n vertices, find a formula for the coronal of H. And it gives the correct answer. Okay, so the correct answer of the coronal of this graph is n over z minus r. And I said, okay, well, let me fact check this. I'll find this in a paper. And I did. So proposition, regular graphs. The notation is different, but that first formula, you can see the chi sub h is essentially the same formula with different letters. I mean, the n and the r are the same. Z shifts to a lambda. Okay. Where did I find this result? Source. It's my paper. so somehow ChatGPT like does not want to acknowledge me, but it got this result, and the way I know it's from my paper is because I was the one that introduced the term coronal. So it would not have known that word at all had it not appeared in this paper. So like you hear these stories about artists whose works have been like sort of plagiarized and taken over by unethically behaving AI bots. I just felt like stabbed through the heart. No, it's not true. I was very giddy that someone, so even ChatGPT had read my paper. So okay, but all right. So it is promising then that it still knows about this stuff, and I did sort of muck around for a while, and I was able to get it to say something wrong. And this isn't just ego being spread out across the room. There's a point to this. So several follow-up questions later. It got all of them right before this one. I asked it this one. Is it true that the spectrum blah 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 blah? And it got to a different answer than I did. So it's got its conclusion at the bottom, which is the opposite of a remark in the paper. I will confess that the first thing I did when realizing that ChatGPT and I got different answers on something was to panic that I had to go retract this paper because it was probably wrong. But I did do a backup calculation. I mean, it's pretty simple, and I'm now convinced that ChatGPT got the wrong answer. Okay, so what is the point of this? The point is twofold. It's the two morals of the story from the first couple of slides. Remember, those were we want to know why something is true, not just that it is true. And we need to think about parameter spaces when evaluating how effective ChatGPT is. And I think this illustrates both of those problems at once. The language on the screen, and I know it's not easily readable by non-experts, it is vague and not helpful. It is exactly the same sort of thing that you get for just regular homework problems when you plug them into ChatGPT and it gives you plausible sounding nonsense. Right? This is like a research level version of that, where instead of training the results, it doesn't know how to get the result, so it just adds text. Okay, so I didn't copy and paste everything, but it just starts spewing this 5 example It's not really an example, and it is just relevant facts. It is just relevant information that doesn't help further the conclusion. So it just gave up and said, well, I better not say nothing, so I'll just say something. The parameter space, I think, is a really interesting one too. We run at our campus the math field day every year. We bring high school students all over the state to solve problems, and we write the problems ourselves. And when writing the problems, you know how like strained you feel in writing them because you can't assume very much from a high school student to know. So you can't invoke theorems from calculus when you're writing problems. There is a skill set of, I don't know, 30 to 50 things, maybe, I don't know how to count them, maybe 100, whatever, of things you can assume they know. And that's in the entirety of what you're allowed to use when writing a problem. Otherwise, it's too advanced for them. That's a small parameter space. And those Olympiad problems, probably the same is true for the computer programming problems and the physics and chemistry and biology problems that the strawberry model took. They're based on that very limited parameter space. Test taking is a skill, and specifically like test taking for math Olympiad problems is a skill. All of the math faculty will tell you that the best students that come to math field day are way better at solving those problems than we are. Right? We can write them, no problem, but they're so good at solving them. Why? Because there's only 30 to 50 skills that they have to master, and they have mastered every combination of putting them together to solve those kinds of problems. And I think that's what's going on with ChatGPT here. It is very good at solving Olympiad problems because there's a small parameter space worth of tools at its disposal, just like Robin's conjecture when there was only 3 axioms, and it's good at doing research. It can troll through the internet, through the internet, and get results and try to string them together. And if they can't find one, then it's done. So it can connect dots quite well. It can write language quite well. With Wolfram Alpha, it can do computations pretty well. And then the question is, well, why isn't that everything? Why isn't that everything that a mathematician does? And is this mathematics? Is this doing mathematics? So the question of, are we in danger of being replaced? Is it doing our job? Is it doing mathematics? And my claim, which is what we're going to sort of move to next, is that it's missing one of the key ingredients. Okay, so it can do computations. It can do like writing up English language description. It's good at connecting together dots that have been handed to it. But I think it's not even that I think, it does not do insight. It does not conjecture new mathematics based on data. And that is, in my view, a substantial part of what it means to be a mathematician. So in the title of the talk, the phrase experimental mathematics, that is not meant as like alternative, that's not the alternative medicine version of mathematics. It is the fact that as part of being a mathematician, we experiment, we collect data, and we make hypotheses, much like other sciences. We just don't need like lab work and test tubes and things to do that. We generate lots of examples, make predictions, write it down as a conjecture, and then try to prove that conjecture. So as a sort of motivating historical example of this, I'll mention one theorem. This one actually really is, I think, understandable enough as content to try to talk about a little bit. Okay, most people are familiar with the idea of a prime number. These are numbers greater than 1, so natural numbers greater than 1, whose only factors are themselves in 1. 2, 3, 5, 7, 11, etc. A lot of number theory, which is the sort of field of mathematics that I'm in, is about trying to understand that sequence of numbers. There is a ... at the end of that list, but it is the most opaque ... Like usually that means like here's how the pattern continues, and this is not that implication at all. We just don't know what is going on in those ... A like thousands-year-old theorem that is one of the most beautiful arguments of thought ever constructed, in my opinion, is that there are infinitely many prime numbers. So that's not for free, right? It might be that there was some last prime number when you kept this list going for a while. But since it's so short, I will just say the argument out loud. So here's the argument. If I give you any list of prime numbers, here's a recipe for making another one, which means you're never done, because then you can do that and do it again and do it again and do it again. Here's the recipe. So suppose those were the only 8 prime numbers in existence. Okay? You multiply them all together. Now you got some big number. It's definitely not prime because you got lots and lots of factors. But add 1 to it. If you add 1 to it, maybe you get a prime number, maybe you don't. But if you don't get a prime number, you could factor it. And the factors of that number has to be a new prime. If you take a multiple of 17, like those 8 things multiplied together would be, and add 1, it's no longer a multiple of 17. It's no longer a multiple of 23 or 13 or 11. So when you factor that number, the product plus 1, it's got to be a new. And you just do that over and over again. You never stop generating primes, so there has to be infinite. Okay, but then the second half of that sentence might cause you to say, well, you just told me there was infinitely many. How can you now ask me how many? Well, one thing we do when we quantify infinities in mathematics is think about relative size. So evens versus odds, we sort of roughly agree that there's the same number of them. Like about half of integers are even, half of them are odd. My intuition does not say the same about prime numbers. It does not feel like half are prime and half are composite. So where's that sort of balance? And one way we can measure this is sort of as like a density. What percentage of numbers are prime? So one way of measuring this is we say this is like the same pi from circles, except we just reuse that letter for something else because we run out of letters eventually. Let pi of x denote the number of primes up to x. So like pi of 1,000,000 means how many prime numbers are there from 1 to 1,000,000. And then what we're going to ask is how fast that function grows. Compare pi of 1,000,000 to pi of 2,000,000 to 1,000,000,000 to 1,000,000,000,000. How does that grow? Every science, every math has this problem where we crunch every historical thing down to one person and we say, this is the person who thought of this and conjectured this. That's a bit of a lie, but for the sake of this talk, I'll say this is Gauss's idea. Gauss conjectured that pi of x grew like x over log x, natural one. So if you plug in 1,000,000, how many primes are there up to 1,000,000? Should be about 1,000,000 over a log of 1,000,000, a couple 100,000 something. And the way they did this back in the day was they made huge books of tables. Like this was just someone's job to like page after page after page of factoring numbers until we learned which numbers were prime, which ones weren't, and write down the prime factorization and count them so that we had data on which we could make predictions like this. Okay, so this is what traditional, and then, as soon as you make the conjecture, it doesn't mean we know the answer. This is just our guess. Maybe once you get to 1,000,000,000,000, the behavior changes dramatically and we have to revisit everything. So it took a long time to get a proof of this, but this is a correct statement. The squiggle, by the way, means asymptotically they behaved like one another. If you take the ratio and let x go to infinity, it approaches 1. Okay, so this is a result that it would be nice to see if we could follow an AI approach to redeveloping. So remember the missing piece that I was claiming was the ability to be inspired by data to make a conjecture, to think of a new potential result that wasn't written down already. Okay, so I'm going to tell you the key ingredient to doing this, but I'm going to have a couple of slides that don't seem related at all. So linear regression. Linear regression does not seem like it has anything to do with primes, and it doesn't, but it's a motivating idea for using regression as a conjecturer, as a tool for making conjectures. And we do this all the time in sciences. You have a scatter plot. You say, you know what? It seems to me there's a relationship between the x variable and the y variable. Let me see if I can write down a line that explains that relationship. That's not so different from what Gauss was doing with his x over log x. But what's different here is, unlike Gauss, where he had to come up with a conjecture of how things might be related, is the parameter space is so small. There's only 2 things you have to specify a line. You have to pick an M and a V. And because the parameter space is so small, this is an exercise that we can give to Calc 1 students or linear algebra students, or Google Sheets does it for free, or Excel will do it for free. You pick a random M comma V line, figure out how bad it is as a function of M and V, and then you minimize that as a Calc 1 problem. What does bad mean? We're going to need this later. So a bad line would be one where the distance from the line to each point or to many points is far away. So you could take the vertical distance squared, add them all up, and that's a good measure of how bad it is. This is a 2-parameter space. And almost every regression that we do in the sciences takes that form, but maybe with more parameters. For example, if you want to do a sinusoidal regression, there are 4 parameters, A, B, C, D. Can you pick values of A, B, C, and D so that that curve goes through some predefined set of points? So if you're modeling anything cyclical, temperature, circadian rhythms, sort of stuff, tides sort of stuff, you plot those points. These are temperatures, monthly high temperatures in the UP, I think, maybe Detroit, I can't remember. I grabbed it from the National Weather Service. But you can find A, B, C, D that minimizes the error terms. Okay, so what we're going to do is we're going to ramp up our parameter space dramatically. And here is the answer to doing this. So this is a machine learning model called Pyzer. The PY part stands for Python. SR part stands for symbolic regression. And we'll explain what that means over the next few slides. But the idea is that we're not fitting 2 parameters. We're not thinking, what are the constants M and B that would make this line good? But we are sort of optimizing over the space of all symbolic expressions. That's our parameter space. It's huge in comparison to 2 real numbers. Okay, so how does this work? You input a set of training data, so that just think the scatter plot points, or think Gauss's page of hundreds and hundreds of prime factorizations. You give it a set of seed functions, like maybe you just like sine and log and x cubed. Maybe those are your favorite functions. I will say more about the 3rd bullet, but every machine learning model that exists, there's a million arbitrary choices you have to make when setting it up, and then fine-tuning those is sort of the art form of playing with machine learning models. And then what this thing will do, remember it's got the scatter plot of all these data points, it's going to output the combination of the functions you gave it, which best models those data points. And again, that's an optimization, like it's not a calculus optimization. Sinusoidal regression, linear regression, those are explicitly computable constants. It's just, minimizing a function of a few variables. This is a more, well, I'll just say it's a genetic algorithm. I'll say more about what that means in a second. But the parameter space is huge. You can just imagine like how many ways there are of combining sine and natural log and x cubed and constants. I didn't specify those explicitly, but it's a +5 here, this multiplication of constants. You can add them, you can multiply them, you can plug them into one another. So there's just an incredibly vast parameter space. So let me say a little bit about hyperparameter tuning. So parameters and hyperparameters, just the jargon is that the parameters are sort of the key inputs to the model, and the hyperparameters are fine tuning. So in this case, like the functions I chose might be the parameters, but the hyperparameters might be making observations that as a mathematician, I know that in whatever context I'm studying, I would never, ever, ever have a natural log inside of a sine. And that might be like field specific. Like it might be that in, I don't know, high energy physics, you see sine of natural log show up all the time. But in some other field of science, surely there are others, that you might not, right? So here your intuition, like your Gausses of the world might say, well, sine of natural log doesn't look right. X over log might sound plausible. So I'll use that to influence my seed functions. Or I may say, you know what, I'm not positive that it doesn't show up, but I'm willing to bet that it doesn't. And so what I'll do is I'll put a penalty to complicated things. I'll put a penalty to natural log showing up in sines, or I'll forbid it entirely in this model. And what one of the inputs to Pyzer, this hyperparameter tuning, is specifying what's unlikely. Maybe you just say you're not allowed natural log and sine. Maybe you're saying you can have a polynomial of the degree of those 3 inside of a natural log, things like that. So there's a lot of like nuances to this. But I wanted to explain how this algorithm works and then give you just in the last few minutes a couple of examples of it spitting something out pretty cool. All right. So here's how it works. Evolution is this sort of discrete evolution is sort of what replaces the calculus part of the linear regression, right? So if you're doing linear regression, you're minimizing the error as a function of M and B. And you're doing that, like you can do that dynamically by changing M and B a little bit and see if your error went down. You do that over and over and over again until you have the perfect line. We do the same thing here. The way Pyzer understands an expression, something as simple as this is as a tree. Right? Trees are actually examples of graphs of the kind from earlier on the top on the four color. It interprets a expression like this as a 1.15 and a y smushed together with a times. That's this bottom chunk of the tree, and it's that and then 0.86 smushed together with a plus. And so, like if you've seen sort of reverse Polish notation on calculators, this is a similar sort of philosophy. It is just unpacking the expression by one operation at a time, what's getting stuck to what. That tree representation turns out to be the key to being able to manipulate it in a systematic way. So one operation you can do to a tree expression like this is take one of your allowable parameters, like plus, and change it to a different allowable parameter, like minus. Okay, and that's a way of saying, you know what, instead of trying this expression, I'll try this expression over there. You can imagine more complicated shifts, like changing a times to an exponentiation, or changing a constant to a whole huge tree. You just plug it in. Which brings me to the second possible. And so that's evolution through mutations. That's one type of transformation. The second one, they really take this genetic language very far. They're like, it's very mirrored on the evolutionary biology side of things. You imagine sort of two different species, and they're sort of swapping DNA, and well, you swap subtrees. So if 1.15y plus 0.86 is a good model, and x to the x is a good model, maybe sort of like smushing them together and merging around like ideas that worked from each would produce an even better model. So that's the sort of evolutionary step in this. You do some swapping, you get the same sort of thing with like letters swapped or variables put in different places, and it's just sort of a free form. Like it's not like an algebra rule that you're allowed to do. It is just trying a related looking expression and seeing if it does better. And then you do this over and over and over again. So here's the sort of feedback loop for this machine learning model. You start with some collection of functions, and over and over and over, what you're going to do is pick a couple of them out, test them out, see how good they are. Maybe then you have a random branching. You pick one of these four paths. Either you throw away a bad one, or you do that mutation step where you just change one of the parameters in one of them, or you do the crossover step where you swap a part between the two things you picked out, or you simplify, which is not always a good idea. So that's why it's not, you don't always simplify. For example, if you have the expression x minus x, of course you can just toss it out as 0, but x minus x might evolve into something better. So sometimes you keep it around. Or you optimize the constant. So that really is the regression part. You could just like, as one of the options in the path, you run a linear regression or whatever regression to make the best possible constant set. And then you replace whichever functions that you improved or you're going to toss. If you've got a new set of functions, you do it over and over. Okay, so this has been very successfully applied in natural science settings. So there's this SR bench, symbolic regression benchmarks, is collections like publicly available collections of data of things that say model the ideal gas law. So it'll be, I don't know, 10,000 data points of actual measurements where you have the pressure and temperature and the volume and number of moles, I guess, or whatever. And it's supposed to guess from that data without any chemistry background, what is the relationship between all those variables? I guess I haven't stressed this a lot, but this is a many-to-one relationship. Your input variables, it could be, this is a multivariate problem. One output, potentially many inputs. And Pizer successfully guesses 7 out of the 9 physical relationships that come from data. So this is it guessing the fundamental laws of the universe just from measurements. It does not get 2 of them right. Pretty interesting. But to my knowledge, this has not been tried out in mathematical settings. So this is sort of what we're aiming to do here. We'll come back to this prime number theorem and see if we can knock this one out. This is a joint work with Eliza Hogan, who's sitting in the audience. This is a project we've been working on, and it suggests a really strong paradigm for how you just go about making new math. Okay, so on the left here, this is Sage Math. This is free open source software. It knows everything about like prime algorithms and things. So for example, here's very, very simple code to just generate pi of x. Up to 1,000, there's 168 primes. Up to 2,000, there's 303 primes. So on and so on. Those are your data points for your scatter plot that you're going to try to fit a function to. And then we just hand those columns of points, those XY coordinates into Pfizer. And we gotta pick, like we can toss it, here's what the code looks like. We can toss it, the squaring function, the exponential function, the 1 over x function, the log function. We'll give it plus and times, and then we'll just let it run and see what it comes up with. It's gonna evolve these equations over and over again. And they're hard to read. But if you process inv as 1 over, then this is 1 over log x minus 1 times x. So if I clean that up, that is very, very close to the prime number. So the punchline is that, once you've systematized this process, this is a 1-minute calculation that took dozens of mathematicians, dozens of years to factor and write down. And it's not all computational. Like the SAGE part of this really did speed things up, but the conjectural part is pretty new. All right, I just have a couple more examples of cool things that work out. The goal of the project right now is to see how much mathematics we can rediscover through the use of Pfizer guessing formulas for things. So one thing we can try to do is reproduce Taylor series. This is a way of approximating functions like e to the x with polynomials. So you just restrict what it's allowed to use. This implementation of Pfizer can use plus and times and powers. And then what we've done for the constraints here is put how complex powers can be. You're not allowed, this is like a complexity limit, these ones and ones. The first one is the complexity of the base. The second one is the complexity of the exponent. All we're going to be allowed to do is x to a constant power. We're not going to allow x to the x or anything like that. And then you run this, and I just want to quickly go over sort of some of the cool answers. If you ask for a Taylor series of e to the x, you might predict that it's not going to get an infinite series, but we predicted you might get the degree 3 Taylor expansion, and you get something pretty close to that. Remember that we're not handing it e to the x, we're handing it several hundred data points of output from the function e to the x, and it gets, 0.996 is not 1, but it's very close. X really is just x. That's very close to a half. A 6 is 0.166. Then, interestingly, it came up with an x to the 6th term. But one thing worth stressing is that this is a random process. Right? Every time we run this, we'll get a different answer out. Like it might not pick up an x to the 6th next time. And I think the last example is I've always wanted to come back and bring this back to the number theory side and model discrete things. So here's a plot of the function x mod 13. What that means is you take an integer, divide by 13, and see what the remainder is. So if I plug in 20 divided by 13, 1 with a remainder of 7. So the remainder is the interesting part. So 20, I get up to 7. So this function just loops up to 13 and back down again over and over again. Here's what Pfizer spits out. If I give it like all the standard functions, e to the x, cosine x, sine x. This is I really like this example because it is the perfect example of this sort of blending of mathematicians' intuition with computer output, because some of these constants are explainable. Periodic functions with period 13, you'd expect some 2 pi over 13s to come out. 2 pi over 13 turns out to be 0.483. That's probably what that means. Negative 3.61, this happens to be the square root of 13. That's probably the correct answer. This is very close to pi over 2. That's probably what that's supposed to be. And this number is very close to 6.5, which is half of 13. That's exactly how much this graph is shifted up from being symmetric around the x-axis. So once Pfizer spits something out, mathematicians can come and say, here's probably what's happening. And then one more thing, which is cosine of something plus pi over 2 is just negative sign of that thing. So we'll apply that trig identity that we happen to know as well. And then the human version is a lot cleaner looking. And it's a really, really good fit. So it's pretty interesting. It does not, for those of you in the room who know what this means, it does not appear to equal the Fourier sine series. The Fourier series, people, again, who know about this, they have these characteristic jumps right at the end. It's called Gibbs phenomenon to make them not model the function well at the jumps. And I don't know if this is a quirk of this one example, but the thought that we might have a different way of modeling continuous functions via cosines and sines and exponentials in a way that doesn't have the phenomenon is sort of an intriguing hypothesis. I don't know if this is new at all. I've never run into e to the cosine x at all in my in my career as a mathematician, except when I'm giving hard calc 1 derivative problems. But it's intriguing. Okay, so I don't have more slides, but I wanted to wrap up with where things might go next. This is the conjectural part of mathematics, the experimental part that I think has been missing from the machine learning world. And there is one more really potentially cool aspect of this that comes up, which is as a community of mathematicians, we're at the very start of the idea of automated theorem proving, where what we do is we take centuries old proofs or modern proofs and try to encode them in a formal mathematical proof system. The leading one of those is called Lean right now. It's the Lean theorem prover. If we get enough theorems into that infrastructure, and we can train a machine learning model to see what new proofs look like and see if it can generate new proofs. That seems to be the leading candidate for how we might finish off that trajectory of have an interesting phenomenon, make a conjecture based on it, come up with a proof. And if we can do that, then we are extinct as mathematicians. I'll end it there. Thank you very much.